Today we're going to talk about limits. Limits is the most fundamental concept in calculus. Like everything above limits, or everything after limits you're going to learn. Everything you're going to learn after limits are all based on this concept. So what are limits? Well, firstly, limits are based on functions. So given a function f of x, it has a limit L. So a function f of x has a limit L if f of x gets closer to L. So it gets closer and closer to L as x approaches A. So the notation of a limit is LIM, which stands for limit, and then at the bottom you have x, an arrow, A, and then f of x, and this is equal to L. Now what this means is the limit of f of x. So the limit of f of x as x approaches A is L. So once again, the limit of f of x as x approaches A is L. We can also visually represent the concept of approaching A using a number line. So if we draw this, okay, that's not helpful. We need a ruler. I mean, we can keep the grid on. Okay. So this is the number line for x. And let's say this middle point here is, or this point here is A. Well, as x approaches A from both sides, both left and right of the number line, so as x gets larger and larger as it gets to A, and as x decreases to approach A, f of x approaches a value of L. Now notice that this doesn't exactly mean f of A is L. That's not true. That's not always true. Because a function has a domain and range. So sometimes A is not in the domain of f of x. So f of A is actually not defined. Other times, however, when A is in the domain of f of x, we know that the limit of f of x as x approaches A is L, right? And that is just f of A. What this means is that we also have a few properties and theorems of limits. So let's talk about them. So the first property we have here is is that the limit as x approaches A, the limit of k as x approaches A is k. Now here, k is a constant, and A is also a constant, and all these numbers here are real. So the second property we have is that So the limit as x approaches a of k times f of x is k times the limit as x approaches a of f of x. So what this means is if I have the limit of x approach as the limit of, if I want the limit of f of x as x approaches 5, or the limit of 6 f of x as x approaches 5, then that would be equal to 6 times the limit of f of x as x approaches 5. Now the third property here is that the limit of f of x as x approaches a plus minus so the limit of f of x plus or minus g of x as x approaches a is equal to the limit of f of x as x approaches a plus or minus the limit of g of x as x approaches a. So an example would be that the limit as x approaches 3 of f of x plus g of x equals the limit of f of x as x approaches 3 plus the limit of g of x as x approaches 3. Now the fourth property is that the limit of x as x approaches a of the limit of f of x times g of x as x approaches a is equals the limit of f of x as x approaches a times the limit of g of x as x approaches a. So an example here would be that the limit as x approaches the limit of if I had this, so the limit of this random function here, so let's say a was 4. The limit of x plus 3 times x plus 5 times x plus 7 as x approaches 4 equals the limit of x plus 3 as x approaches 4 times the limit of x plus 7 as x approaches 4. And then on to the fifth property, which you can imagine we have constant times function plus or minus function times function. The next one should be function divided by function. So the limit of f of x over g of x as x approaches a equals the limit of f of x as x approaches a over the limit of g of x as x approaches a. Now, of course, it's given that g of x is not 0, so the denominator isn't 0. An example would be the limit as x approaches -1 of 5x squared over x plus 2 equals the limit of 5x squared as x approaches -1 over the limit of x plus 2 as x approaches -1. So then we also have our last property, which is a composite function. So what this means is the limit of g of f of x as x approaches a equals g of the limit of x of a as the limit of f of x as x approaches a. So, and this is given. So this is given that g is continuous, or the function g of x is continuous at x equals the limit of as x approaches a of f of x. So what this means is that this thing is true given that the value of g of x when x is this number inside is like exists. So if this number here is L, then this would be g of L. So this equation is only true if g of L actually exists, right? So an example here would be the limit as x approaches 5/3. So the limit of say x plus 3 times or 4 times x plus 3 squared would be equal to 4 times the limit of x plus 3 as x approaches 5/3 squared. Now here we don't see f of x or g of x, but we can pretend that f of x, so we can let f of x equal x plus 3 and g of x equals 4x squared. So that's about the main properties, but using this last property over here, this one, we can derive a few new properties, like subcases, special cases of this. So using this, we know that the limit of f of x to the power of m as x approaches a is gonna be the limit of f of x as x approaches a to the power of m. And an example would be the limit of 5x to the power of 10 as x approaches a equals the limit of 5x as x approaches a to the power of 10. And the second theorem we can derive, the second subcase we can derive from this theorem here is that the limit of f of x root m, or you can say the limit of f of x to the power of 1/m, which, because those two are the same thing, equals the limit of f of x as x approaches a to the power of 1/m. For example, the limit as x approaches a of the cube root of x plus 5 equals the cube root of the limit of x plus 5 as x approaches a. So these are all the properties. Now let's solve a few simple problems. So let's first solve limits where a is a real number, that is a constant. So by this I mean very, very simple problems, like the limit of, so these problems are all from, so these problems and definitions are all from the NSS Mathematics in Action Module 1, Calculus and Statistics. So this is problem 5 in exercise 3b. So it says, what is the limit of 18 as x approaches 4? Well, using our property that, we can solve this using the property that the limit of k as x approaches a is k. We know that the answer here is 18. The second problem here is, so this is 3b, exercise 3b. Problem 5. And then another example here would be the limit as x approaches negative, the limit of x plus 1 over 2x minus 3 as x approaches negative 2. We can evaluate this using the property that the limit of f of x over g of x as x approaches a equals the limit of f of x as x approaches a over the limit of g of x as x approaches a, given that g of x is not 0. So this means that this is equal to the limit of x plus 1 as x approaches negative 2 over the limit of 2x minus 3 as x approaches negative 2. And then we can evaluate this using the property that the limit as x approaches a of f of x plus g of x is, never mind. Okay, so wrong property. Okay, we can evaluate this using the fact that we know that the limit of f of x as x approaches a is equals f of a as long as a is in the domain of f of x, or you can say f of x is continuous at x equals a. Or basically you could say this is true as long as f of a exists. Well, let's say f of x was x plus 1. Then as x approaches negative 2, f of negative 2 would be just negative 2 plus 1. And we do the same for the bottom. We have 2 times negative 2 minus 3. So here we have negative 1 over negative 4 minus negative 3, which is negative 7, which is 1 over 7. And this is problem 9 on exercise 3b. So other problems that we might consider are harder ones, such as when we have f of x over g of x, but g of x is 0. So an example would be evaluate the limit of x plus 1 over x squared minus 1 as x approaches negative 1. Now here we want to use this property, but this is built on the case that g of x is not 0, because we don't want 0 as a denominator. Now here, if you plug negative 1 in here, we know that we have 1 minus 1, which means that the denominator x squared minus 1 is 0. So we can't just use this theorem anymore. We have to do something else. So what we can do is we can factor out x plus 1 times, so x squared minus 1 is x plus 1 times x minus 1. And then we can cancel x plus 1 out. Why? Because we know, so why? Because isn't negative 1 plus 1 0, so won't the denominator be 0? Well, yes, but we're looking at when x approaches negative 1. What this means is that x gets closer and closer and closer to negative 1, but it never gets there. But it never actually reaches negative 1. So up here we know that this property can be used because as x gets closer and closer to a, we know that f of x will get closer and closer to f of a, and eventually it will equal something that is no more different than f of a. But here we know that when x approaches negative 1, when x approaches a, when a is negative 1 and x approaches a, f of a does not exist. F of a is undefined because when x approaches negative 1, f of a has a denominator of 0. So f of a is undefined. So we can only estimate the value of f of a as x gets closer and closer to negative 1. Like, we can use a calculator and actually set x as negative 0.9999 or negative 1.1111 or 1.00000001. We can't actually calculate this when x is negative 1 because this doesn't exist. So in this case, when x is never even going to equal negative 1, we can just cancel these out because this is only 0 when x is negative 1. So now we're left with the limit as x approaches negative 1 of 1 over x minus 1. To evaluate this, we use the theorem above. So this means that we have the limit of 1 as x approaches negative 1 over the limit of x minus 1 as x approaches negative 1. So what this gives is 1 over negative 1 minus 1, which is negative 1 over 2. And this is problem 22 from exercise 3b. So next lesson, we'll try and cover limits at infinity. So right now, this here, a is a constant. Next lesson, we're going to let a equals positive or negative infinity and see what happens.